PhD student in UCLA, and I am working on the next generation liquefaction project, and I'm focusing on the liquefaction susceptibility part. And at the morning session, Professor Stewart explained that we need new updated models used as prior to triggering and consequences models. And it is kind of like an important part of the liquefaction because it is the start point. We kind of need to understand the fundamental characteristics of the soil so that we can move forward and analyze the consequences based on the selected assessment types, which are dependent on the susceptibility. Before going to the details, I just wanted to thank the support of peer and FHWA who supported this project. And also, I would like to thank my research team, my advisors, Professor Brandenburg and Professor Stewart. We have Professor Kramer from University of Washington, who was really helpful. We have Dr. Amalesh Jana, Professor Studline, who gave a presentation today, is really helpful, Professor Evans, and Dr. Almer. For today's talk, this is my outline. I will just briefly talk about the aim of the next generation liquefaction project. Then I will move on to the existing susceptibility models. The reason why I discuss these, I'm just going to use it for the framework that we are going to illustrate today. Then I will discuss the logic tree framework that we suggest to use the susceptibility to use for the seismic round evaluations. Then I will illustrate it with a case history from 1999 Kocaeli earthquake. Then we will apply the logic tree framework to this case history. Let's start with the aim. Professor Stewart explained the aim of this project, but in detail for the NGL susceptibility project, we are trying to create a huge database. We gathered over 500 laboratory test results, and we are distinguishing the susceptibility portion from the case history. So we are only using the laboratory test results. As an NGL vision, we are trying to make our assessment probabilistically, and for susceptibility we are using our inherent soil characteristics, which are Atterberg limits or from CP results IC. And I think it's a good time to define the susceptibility. And susceptibility is the potential of a soil to experience significant pore pressure generation and strength loss evaluated as a fundamental material characteristic. So susceptibility is, in our definition, is independent on the loading conditions and is independent on the soil state itself. Let's move on to the existing susceptibility models. There are two most commonly used models, which are Bray and Sancio 2006 and Boulanger and Idris 2006. Bray and Sancio uses water content over liquid limit and PI as their model, and Boulanger and Idris uses liquid limit and plasticity index in their model. You can see the comparison of these models in liquid limit plasticity index here, but it should be not that we should note that Bray and Sancio was using water content over liquid limit in their criteria. So so this criteria depends on a certain exceedance of water content over liquid limit. So if we check on a particular PI value based on these two models, they can yield significantly different results. So that is the reason in our illustrative example, we will go into detail of that. So during the 2023 peer workshop, these two models are discussed extensively, and their authors, Professor Bray and Professor Boulanger, explained their aims with these models. Professor Bray explained that the aim of their model is to capture if the hysteresis loop is similar to the ones that liquefy or not. Professor Boulanger explained that their aim is to select a cyclic strength assessment type. So, and their consensus about the models, if there is a chance to sample a high quality undisturbed sample, sample it, go to the laboratory and cyclically load it and test it and use those results. And after this workshop, participants wanted to form a database, which we tried to do that, and the database is still expanding. So we are including laboratory test results, both cyclic monotonic test results. We have index properties and the CPT results that are co-located to these laboratory tests. And based on this database, we are aiming to develop a liquefaction susceptibility model that is dependent on the material inherited characteristics, which is going to be a probabilistic model. Let's move on to the logic tree framework. So the logic tree framework that we are suggesting has 3 phases in general. So you start with a soil unit, and for soil unit, you're selecting a susceptibility model. This model might be Brian-Sancio 2006, it might be Boulogne-Idris, or you can select both of them. Or in the end, when we have a susceptibility model, you can use that one too. So we can use multiple models with this logic tree framework. And as the first phase, we can assess the soil body to susceptible to what is the probability of susceptible to liquefaction and what is the probability susceptible to cyclic softening. And this phase is followed by the triggering or cyclic softening, where we can use multiple assessment types. And as the last phase, we can use multiple consequences assessments. We can have multiple consequences such as lateral spreading. We can have excessive settlement. And all of these phases are connected by weights, which are going to be the probabilities. So let's discuss the case history that we are going to illustrate today. It is a site from 1999 Kocaeli earthquake, which is already included inside the NGL database. And there is a boring 5 meters apart from a CPT, which is presented here. And there are multiple specimens taken from the boring. And we are investigating the layer between 3 to 4 meters. The reason why we selected this layer is the PI is around 10, which is in the region where these 2 susceptibility models will yield to 2 different results, which I will show you in a minute. Let's apply the logic tree framework. As the first phase, we selected both of the models. We are going to evaluate based on Brian-Sancio and Boulogne-Idris. And if you apply, if you enter these models with PI 10, Brian-Sancio will result in susceptible to liquefaction. Since it is deterministic, there is no probability there. Boulogne-Idris 2006 will yield to clay-like behavior. And if you use the converted versions of these models discussed in Huang's 2008, the probability of susceptible to liquefaction is going to be 100% for Brian-Sancio, and it's going to be 0% for Boulogne-Idris. So they yielded totally different results, totally the 2 end behaviors. Then we can move on to phase 2, which is the triggering assessment. We are using 2 different models, Boulogne-Idris 2016 and Moss et al. 2006. This is the results coming from the CPT right here. And I just want to point out that the QC1N is around 10, but the fines correction is around 55. This is showing the importance of fine corrections inside the triggering models, which is discussed by Varun in this session. And when we enter these models, we can find that cyclic resistance ratio is 0.12 for Boulogne-Idris and 0.05 for Moss et al.'s method. For phase 2, we have to perform cyclic softening assessments too, because Boulogne-Idris 2006 susceptibility model yielded to susceptible to cyclic softening. So we are using Dahl et al.'s 2018 method. We can find out the tau cyclic over SU as 0.7. And we can estimate SU based on Shansep's suggestions as 36 kPa. We know that this layer is possibly overconsolidated, and we have estimated as 4. And we can find the cyclic resistance ratio is around 0.54. Then we perform some corrections for field, which comes out to be as 0.44. And you can notice that the triggering assessments and cyclic softening assessments yield to 2 different results, which one of them is 0.44, the other one was around 0.05 to 0.12. Let's apply the logic tree framework. So at the first stage, we can enter both of the models. We are assigning 50% weights for both of the models. For the Brian-Sancio, we found out that the probability susceptible to liquefaction is 100% and 0% for susceptible to cyclic softening. For Boulanger and Idris, it is the other way around. For triggering assessment, we are again assigning 50 to 50 for both of the triggering models that we used for this example, and we are directly using Dahl's 2018 model for cyclic softening. And the results indicate that if we use Brian-Sancio, the resistance ratio is 0.09. If we use Boulanger and Idris, the cyclic resistance ratio is 0.44. So there are 5 times of difference in both of these, between these 2 models. And if we use a framework that combine these results by using this formulation, the first part allows us to use multiple susceptibility models. These weights allows us to assign probability of susceptible to liquefaction and susceptible to cyclic softening. And these portions allows us to use multiple triggering and cyclic softening models. And for case 1, we can combine them and say that the cyclic resistance ratio is 0.26 based on the suggested logic tree framework. But for one engineer, they can say that the Brian-Sancio, I'm just going to use Brian-Sancio and find out the CRR is 0.09, and another engineer can say the CRR is 0.44. And I just wanted to note that the calculated CRRs are just for the usage of estimating the cyclic resistance ratio. If someone wants to use it for consequences, individual CRRs should be used for factor of safety estimations, and consequences can be combined in the end. So luckily, Dr. Sancio and Professor Bray performed some cyclic tests on these samples, which one of them is presented here. And the results indicate that the CRR is going to be around 0.35 after some field corrections. And we have decided to use these laboratory test results to estimate we are just going to use these lab results as a susceptibility model, and we are just going to investigate some features of the cyclic test results. The first thing to notice is P prime approaches to 0. There is a high modulus degradation that is observed. There is high pinching. It has a banana-shaped loop, where we use this terminology for sand-like behavior. There is steady to rapid increase in strain accumulation. So if we consider all of these behavior characteristics, we found out that it is going to almost have a sand-like behavior. And we have decided to assign the probability of susceptibility to liquefaction as 90%. And now, since we have a third model based on our lab results, we can use it in our logic tree framework. So we have Brian-Sancio's, we have Boulanger and Idris's, and we have the lab model. We are trusting the lab model more because Like I said, if it's possible, just sample it and perform a cyclic test results. Then this is the assigned probabilities. Now we can use laboratory test results to estimate the cyclic resistance ratio 2, which is assigned for both the triggering and cyclic softening assessments. And when these results are combined, we can find out that the lab model yields to 0.26. When cyclic resistance ratio from laboratory test results are also included, Bray-Stancio yields to 0.24 and Boulon-James yields to 0.39. In general, the cyclic resistance ratio is found to be 0.27 when the logic tree is applied, and it is worth notice that it is very close by to 0.26 when we do not have the laboratory test results. But that is just like a weighted average. We always trust the laboratory test results more, so we trust the case 2 more than case 1 in this case. So to conclude my talk, the logic tree framework allows us to represent the effects of preceding phases to the following phases. So susceptibility affects triggering, and triggering assessments is going to affect the consequences. When laboratory tests are available, it provides a more reliable estimation. In this case, it didn't yield to very different results, but for some cases it will. So having a laboratory test result is always a good practice. When we have more information coming out from the cyclic test results, it is easier to understand the behavior of the soil body under the cyclic loading. And also, I just wanted to mention that we have over 350 cyclic direct simple shear results and 145 cyclic triaxial results, which are currently increasing with entering more data. But we are in the end of our creation of the database, and we have more data than previous models. And all of this data is publicly accessible. And this is the QR code to the link where you can just create an account in NGL and see all the lab data by using a lab viewer. There's a download button. You can download all the data and use for your own research. Thank you for your attention. If you have any questions, I'm glad to answer them.